Good. So during the break, a number of you came to ask a little more about how does one calculate actually these transfer functions, and especially using these power spectral densities. So I gave an explanation, and I think everybody should listen to that. In mathematics, you learn a lot about signals that have a finite energy. What is the energy of a signal? It's x squared dt integrated over time, and the typical functions that you study in mathematics have a finite energy. As a consequence, they have also a finite Fourier transform, and you can do a single Fourier transform on the signals. However, even the simplest signals that we are interested in do not have a finite energy. For example, a sinusoid has an infinite energy, and all the signals, vibration, the signals in acoustics are not finite energy. However, there are finite power. The power is finite. This is true for most of the signals that we are interested in practical applications in whatever. And so for such signals, you cannot use a single Fourier transform. What you have to use is the spectral analysis in the sense of Wiener. Wiener developed that method, and of course, it's now widely used. How does that go? What is decomposed in terms of frequency is the power. You take the Fourier transform of a signal that you have, but on a finite window, which is just equal to t. So you take the Fourier transform, square it, divide by the period t, so that you have this t here. And then you take the limit as t goes to infinity. But if you do that, it's not statistically stable, and you have to average. So in fact, you have to do some ensemble averaging. So how do you do that? Because you don't have ensembles of signals. What you do is you take your signal. So here is a signal, which is infinite energy, finite power. You divide the signal into blocks, and you have here m blocks. You have to have a certain number of blocks, and you consider that these blocks give you the ensemble, so that when you calculate your spectral estimate, your power spectral density, what you do is you take your Fourier transforms. Now, these Fourier transforms here are done by fast Fourier transforms. You square that, then you sum over all the blocks, and then you divide by the number of blocks. And in fact, you have to put a factor delta t over n, which comes in because this discrete Fourier transform has to be related to this continuous Fourier transform. So that's a detail. So this is the expression that you use. And typically, you take, for example, n is equal to 124. So typical numbers is n is equal to about 1,000. M is equal to perhaps 100. So you need perhaps something like 100,000 discrete samples. And once you have done that, you average, and this gives you a statistically stable spectrum. This is what you do on velocity signals. This is what you do on pressure signals. What you should do. But in many cases, you see people who just do a single Fourier transform. And you see a lot of tones appearing in this Fourier transform, but they are not meaningful. What is meaningful is what is done here. It's not meaningful to just not average. You can do the experiment on your computer. You will see statistical averaging is compulsory. Once you've done that, you have also to do that for the cross power spectral density. You take the signals x and y. So here is the Fourier transform of x. Here is that of y that you conjugate. This is in the block G. and then you sum over all the blocks, and you have to divide by t, but then you put this delta t over n in front of that, and a few other details. And here you have the cross power spectral density. Again, what you learn in books, in controls, for example, is that you have a signal x of t. This is the linear system, and you get y of t here. And to get the transfer function, you take the Fourier transform, divide by x of f. But this doesn't work for us because our signals are not L-square integrable. What works are these expressions. H of f is equal to the cross power spectral density divided by the power density of the input. And if you want to get the gain alone, H of f square is equal to that. So these are results that we use for our signals. This is, yeah.
How do you calculate the uncertainty of a power spectrum?
How do? Oh, the uncertainty. So there is a whole theory behind that, but what we do, we have seldom used that because you see that you become stable or that you still have a lot of oscillations in your spectrum which are not meaningful. I'm insisting because I see a lot of papers like that. Unfortunately, this is not very well known. It's fundamental for those who do any spectral analysis. This is how you should do it, but it appears that this is not widely understood, especially perhaps because it's not well taught by mathematicians. They don't understand that we don't care about L-square integrable functions. We care about power, finite power signals. This is our ambition to study finite power signals. We are not interested in finite energy signals. We are interested in finite power signals. All right, so this is a digression, but it's important. This is what I learned from experience. Nobody taught me that, but I'm teaching that to you. So be very careful. If you do calculations, again, it's very tempting to take your 1,000 points that you have in your calculation and do a Fourier transform and say this is the spectrum. It is not. It's not. You have to, so it requires sufficient amount of data points to get a power spectrum. Now there are other ways to do power spectral density, which are more sophisticated and I cannot explain now. All right. So here is the next thing is to look at some systems and in particular look at some simple instability problems. We've done that in a theoretical framework yesterday, and here we want to actually apply what we've learned in very simple systems which are well controlled. So the case that first of all, it's always good to look at basic material. So here it is. Very often we study systems which are confined, and we've learned that the Rayleigh criterion is important, and if this is positive, there may be a possibility of instability. The frequencies have to match, the phase has to be in the right position. The mechanics of these instabilities is that heat release produces pressure and velocity fluctuations which induce heat release, and this heat release feed back again, and a loop is closed here. We've seen that this happens in domestic burners. We studied cases where the flame is in fact sitting on the burner, and this becomes unstable. Actually, a manufacturer of devices for heating paper, you know, in the processing of paper, you need to heat the paper, to get the water out? Well, these devices are rather powerful. They are made of perforated plates, ceramic perforated plates. And when they start the process, it makes a very loud oscillation, very strong instability, very difficult for workers in the manufacturing plant. And so they came to us to see how we could actually help them eliminate this oscillation. And this is why we started working on small flames, perforated plates, and so on. You have various other experiments like this one here, where the flame is more or less confined, or the piston is moving here, and so there is an interaction between the flame and this piston. Well, anyway, so here is a simple system first to begin with. It's the burner. In this case, there is no loudspeaker anymore, but we can place a microphone at the bottom. And we have here a plate at the top. It's cooled, and so the flame interacts with the plate. There is a photomultiplier. Gas is introduced in this burner, and we have explored various sizes of this burner body, and the equivalence ratio in this case is fixed, and we change also the velocities. And what we see is that by just simply looking at the oscillations, in some cases you have no oscillations. This flame is stable, and you see something which is very stable like that. And this depends on the plate position. But if you change the plate position, there are cases where you become unstable. You have a higher value at the microphone, and you see that the regions for stability are rather small, and in most of the time, you have situations where the flames are interacting with the plate, and this produces sound. And what you see is this wrinkling of the flame. When you are here, you have two wrinkles like that, and this is, of course, dynamic. And if you are here, you have three like that. And if you are here, you have a number of these oscillations taking place. So it's a simple experiment, and you would like to explain that. If you are able to explain that, it's already a step forward. If you are not, again, how will you explain the complicated turbulent combustion situations? So it's always a good exercise to try to see if you can solve simple problems. And what is the evolution of the frequency? What is seen is that there is this sort of ramp-like evolution. You see in certain places you have very little, but the frequency has gone down here and suddenly jumps back again here. It's here, jumps back. And the frequency is around what? What sets the frequency here? You've seen the shape of this burner. You see the burner has this shape. It looks like what? Like a bottle. And the bottle has when you blow on a bottle, it makes a resonance. It's called the Helmholtz resonance. So this case is a case where you have a flame sitting on a Helmholtz resonator. So the Helmholtz resonator has to be studied. So this is what we are going to do. And afterwards, we have to put in what we know about the flame and how we model the flame. So the resonator is like that. We have a volume, and there is a pipe. Now, the small difference here is that there is flow across this resonator. Usually you don't. Usually you have just this is closed, there is no flow. But in our case, we have flow. There is a jet coming out of the resonator. And let's call this section 1, and this is section 2. And in the air, let's say this is section 3. 3 is the, for example, here it's the pressure outside the jet. P prime, P, we will use later the pressure P3. So here we have pressure P1. Here is pressure P2. And this is pressure P3. And inside here, the pressure is P1. We consider that everything is homogeneous here. The mass inside this volume is rho multiplied by the volume itself. This is the section, S, and this is the length, L. So we want to look at the dynamics of this system. And the little difference with the standard resonators is that we have the flow. So now, the first thing we write is we take this part between 1 and 2 and write the momentum equation. What does that say? It says that the mass that is contained here, rho L times S, this is the mass, multiplied by the velocity dV by dt, is equal to the pressure P1 minus P2 multiplied by S. And then, so this is just explaining that the forces which act here produce acceleration of the flow inside this duct. We will transform that into fluctuations. We are interested here in fluctuations, so this is rho L S dV prime by dt is equal to P prime 1, the fluctuation pressure at section 1 minus P prime 2 times S. Next, we have this jet, which comes out here, and between the pressure P2 and the pressure P3, which is in the atmosphere, we have the Bernoulli theorem, which tells us that P2 minus P3 is equal to 1/2 of rho V squared. And this can be transformed into fluctuations. P prime 2 minus P prime 3 is equal to rho V bar, so that's the flow velocity in the jet times V prime. And so the pipe and the jet, these two equations can be combined, and they give. You see, I take this one and that one and combine them, so I have to actually multiply this one by S. So we multiply this by S. And then we add them up so that what we get is rho L S dV prime by dt plus rho V bar V prime S is equal to P prime 1 minus P prime 3 times S. So this is the pipe and the jet. Now we have to cope with the volume, and what we can say for the volume is that dm over dt is equal to the flow out of the volume, which is minus rho V times S. And M itself is equal to rho V, so that we can write that expression and divide by rho, we have 1 over rho d rho by dt. We have v in front of that is equal to minus Vs. And inside this volume, we consider that the transformations, the fluctuations are isentropic. Nothing is here to make it different. There is no viscosity, no conductivity, whatever. And so we can say that immediately that 1 over gamma p, so everything is isentropic. It means that p over rho gamma is equal to constant. So dp over p minus gamma d rho over rho is equal to 0. And so 1 over rho d rho by dt is 1 over gamma p dp by dt. So that expression here becomes v times divided by gamma p dp by dt is equal to minus Vs. And we can transform that into fluctuations. So this is p prime, and it's the p prime at 1. This is the p bar. It's the pressure inside this system. And this is the equation for the volume. And now we can combine these two, and you see we combine the equation for the pipe and the jet, and this equation for the volume. And to do that, we have to differentiate this with time. So rho L S d2 square v prime by dt square plus rho v bar dv prime by dt times s is equal to dp prime 1 over dt times s minus s dp prime 3 over dt. So what will be driving actually this resonator will be this term, and this one will be replaced by what is here. So you see that this will be minus gamma p bar divided by v s, and this is a v prime now. V prime and maybe there is an s square here. I'm not quite sure. Yeah. Minus s dp prime by dt. And so finally we have an equation. We can actually drop some of the areas here. We have an equation for this resonator. And with the right-hand side, the resonator is driven here by the pressure. So we have something which looks like rho L d2v prime by dt square. It's a second order equation plus rho v bar dv prime by dt. So the flow is damping here. The flow acts as a damper, plus here gamma p over times s divided by v times v prime is equal to minus dp prime by dt. There may be something wrong in what I've just derived. Let's see. So this is the let's see. Yeah, typically the resonator, if you do experiments and you want to study something like that, it's very simple. You take on one side you put a microphone, on the other side you put a loudspeaker, and by looking at the microphone at the bottom of this system, you draw the level of amplitude of the system. And so you scan the frequencies and you see an acoustic response of this oscillator, and there is a response around 200 hertz, which is the frequency that we just saw in the experiments. So basically this oscillator is governed by this Helmholtz resonator. Now, in fact, here we have a nozzle, so it's not quite like a standard resonator, but that can be accommodated by actually using a length L, which is effective, and which is this the size of this exhaust divided by the size of in the nozzle, integrated over the nozzle, plus an end correction. I told you that there is always this end correction, so you put an end correction, and so the angular frequency corresponding to this Helmholtz resonator is given by this expression here. There is a row missing. I don't know where it came out from. Yeah, probably somewhere in between here. So there is, let me put it here. The row is here. So somewhere in the calculation, I missed the row, but nobody told me. But anyway, I missed it. I missed it from there. You know, it must be here. Must be here. Yeah, you see the row is somewhere. Somewhere is a row. I don't know why it doesn't show up, but I think it's there. And what you see is that the frequency, the resonance frequency appears here. Omega 0 square is C square times S divided by V. And also another point which is missing is the L. The L is here, so we have to divide by L. So this is, yeah, you have to bring this L down, so it comes here. So let's put it down immediately, like that. It comes in here, and it comes here. So maybe perhaps by using this row here. So maybe that's what's wrong. So, well, I wanted to show you that it comes out that you can actually obtain that with some simple calculations, but there are perhaps a few mistakes here. So 1 over L is here. So this is the resonance frequency which comes in here. C squared times S divided by VL. And so now this is how the system looks. In this case, it's written a little differently. In addition, the notation has been changed a little. The pressure P'1 is now the pressure at the exhaust. It's bad, but unfortunately, that's how it looks. But basically, it's a differential equation, and you have a driving term on the right-hand side. And so the whole problem is now to express the pressure due to the flame and to close the loop in this way and have this equation which will give you the dynamics of the problem. So you can express that like that. It must be very close to the equation there. You see the velocity V'1, and the pressure which is there, this term, the right-hand term, is now the problem. So the resonator is driven by external pressure fluctuations at the burner outlet. Are there any questions here on this? And now, what is the pressure? Well, the pressure we learned from a lot of previous material that the pressure looks like that. You can relate the pressure to the heat release fluctuation. And there is as you radiate pressure, there is also a time lag coming from acoustics, but usually it's very small. Now, the heat release itself can be observed using a photomultiplier, and you look at the intensity. Or you can use the area. And by using this expression, you have something which tells you what is the pressure. And so what you can say is that the pressure is related, for example, through a constant here, to the area changes that are observed. And you do observe area changes during the process. There is a small delay, which is due to acoustics, because these area changes are reflected at a later time because of a very short time. This tau A is very small because the whole system is not large. So this is the pressure radiated. It's radiated back to the resonator. And indeed, what you see here is the CH signal. The microphone is here. And if you differentiate the signal, the intensity signal, both of them match pretty well. So the acoustic pressure, the time derivative of the heat release are similar, confirming that the source is suitably identified. And now, what you can say is that this area itself is some sort of replica of the velocity fluctuation at the exhaust of this system. What is the time lag? Well, it's a delayed version of this velocity with a certain time lag. And this time lag, what is it? It's actually the time it takes to a perturbation coming here to get to the plate. So it's like Z, so like that, the distance between the plate and the burner gets into the system, divided by the velocity V1 bar, the mean velocity. So here you have a model. Of course, you don't know this quantity here, what is the relation between V prime and A prime, but they are related. And so now you have a complete model. This is the resonator. Here you have the pressure variations. The pressure is given in terms of the area. The area is given in terms of the velocity. And like that, you have here a term which is also given in terms of the velocity. And it's the second derivative that comes in. It's a delayed version of that second derivative, and you have this, the time lag that comes in here is a convective time plus an acoustic time. And so you can lump all the parameters in front of this term into a big N here, which is just all that. And then you have this term here, which you write like that. It's nicer if it's written in that way. Tau A is very small compared to tau C, so tau C can be given. Tau is nearly tau C. And so omega 0 tau, this equation has a solution at the resonant frequency F0 if this quantity is equal to that, where m is equal to 1, 2, etc. And this imposes a condition on the convective delay. So you find here the delays which will provide instability. So these are 3 pi by 2 for these quantities, modulo 2 pi. And so this explains why the system will have regions of stability and regions of instability. And this will be, of course, related to the distance between the plate and the burner. And when you take this expression and you use it here, you actually get this is what is observed, and this is what is what is observed in terms of what is it? Phase. Yeah. So basically you can see that what is being obtained here for the time lag corresponds to the place where you see the 3 pi by 2, or actually corresponds to these points here. So you actually predict these values for the resonance, and it can actually resonate not only at those points but around it, and this of course depends on the level of damping. Now the damping here is essentially given by the flow. It's the flow which enters here in the resonator. The fact that you have flow introduces a damping here. And when you do calculations with these parameters, you actually find these frequency changes as a function of F0 is the frequency of the resonator multiplied by tau. This is dimensionless, and you see that you have this sort of behavior, and this is actually what is observed experimentally. You see the experimental points are here, and so you do represent. So now the calculations give you much more than what is actually being observed here. So it matches, not quite, but reasonably well, and it describes this change in frequency that is observed when you change the position of the plate. So what is the conclusion is that you have instabilities which occur with this rather unconfined flame, and you can explain these instabilities using a model for your resonator. In this case, it's a very simple resonator. It's driven by the pressure oscillations. These pressure oscillations are related to the heat release fluctuations, which are themselves related to the velocity fluctuations which come out from the resonator. So the loop is closed, and you have a system. It's a real system. You can explain to a good extent with a few parameters. You've seen at various places we didn't have a complete physical process there, but with a few parameters you can explain what is observed here. And in addition, the mechanism which produces variations in the flame surface is the interaction with the plate. It's the fact that the flame interacts with the plate. Flame wall interactions could play an important role in the development of combustion instabilities. But this little problem here is more to show that by putting all the pieces together, you get an explanation of this unstable behavior. All right, so we have some time for questions here. I think we are not going to take the next topic, which is again one of these problems, but let's perhaps have questions before we stop. We take a picture of all of us. I'll change my shirt into one of these T-shirts. Yes.
This goes back a little bit, but in the demonstration you showed of the M plane versus the V plane, I'm curious, was there a change in the forcing frequency, or what caused the M plane to transition to the V plane in the video?
In the video, the question is what caused the M flame to transition to the V flame and vice versa. It's a magical stick. You've seen the Daniel Durox comes with a stick and brings the flame there, and so you see that for the same conditions, you can have a stable flame which has an M shape, or you have a stable flame which has a V shape, and this is observed in practice. You have situations where the history determines what you have. this is a good example to show that flames are not unique. For the same operating conditions, you can have multiple solutions. So this is what we know. Now, what happens is that these two flames respond differently because the mechanisms which modify their shape are different. In one case, it's mainly, now, when you put no fluctuation at the bottom of the system, nothing happens. The M flame is stable. But as soon as you put a fluctuation, the flame responds, and there is this interaction between flame sheets, which produces an annulus of fresh material, which burns and produces a strong pulse of pressure. In the V flame, the interaction takes place with the vortices. You shed vortices from the lips. These vortices are synchronized with by the acoustic field, so they come at a given rate. They are convected to the flame, so you have a time lag. In fact, the next problem is just to study that. Yeah, you see let's just put that on like that. You can see that. You see this is just to study this V flame. And again, it's, let's pass that. So basically, this is the device. There is no loudspeaker here. We now look at the instability, but yeah. And the point here is that the process is due to the convection of vorticity into the flames, interacting with the flame layers, like what we've seen in the forced case. This is what happens in the free case. The vorticity is produced at the lips, convects to the flame, and wraps the flame, produces a pulse there. This is returned back to the resonator, and you can write a model like the previous one in this case. It's somewhat very parallel. We did these studies at about the same, in the same years. So you see you have this self-excited flame which appears here at 172 hertz. Of course, it depends on the size of the resonator, and so by changing the size, you can change the frequency of resonance. And this happens because you have this convective time. So the delay here is due to the convective time. You see you have what is shown here is that delta Q over Q, the fluctuation in the heat release, is basically related to the fluctuations in velocity. So by fluctuating the velocity here, it produces vorticity which reaches the flame tip, and this will produce heat release fluctuations, and this will come back through the pressure term, which is shown here, and will drive the resonator. In fact, here we even know the transfer function. This is how the transfer function was measured, and you see that the gain is not very large, but it is sufficient. So if you adjust your resonator in this range, you may have more chances to get instability. And what you see here is that the oscillation, the intensity oscillates, and you can say, well, it is due to the velocity perturbations with a convective delay. And this is the mechanism. You send vortices. These vortices are rolling the flame, and you have these sheets which are disappearing, and so there is emission. So this is at 150 hertz. Now you have many vortices. You have 3 vortices here. And this is how it looks. Whoops, it's done. So anyway, tomorrow we'll see that in further detail.